Hello, so today we are going to solve this problem called Game of Life. It's part of Leetcode Daily Challenge. Leetcode April Challenge. So the problem is basically about the Game of Life, which the rules are described here. So we have m by n grid of cells. Each cell has an initial state, which is either live or dead. Live is marked by the value 1, and dead is marked by 0. And each cell interacts with its neighbors, and we have 8 neighbors. We have the neighbors horizontally, so left and right, vertically, so up and down, and then diagonally, all 4 sides of the diagonal. So the rules of the game are that any live cell with fewer than 2 live neighbors dies. So basically, we look at the state. If it's equal to 1, which is live, and we count its 8 neighbors. If it has less than 2 live neighbors, so less than 2 neighbors of value 1, then it dies, which means we set its value to 0. The second rule is that if a cell is live and 2 or 3 of its live neighbors and 2 or 3 of its neighbors are live, have value 1, then the cell lives, so we keep its value at 1. The third one is any live cell with more than 3 live neighbors dies. So if we have a cell that is live and we count its live neighbors and they are more than 3, then we set its value to 0. The last rule is that for a dead cell, which is a cell that has value 0, if it has exactly 3 live neighbors, then it becomes a live cell. So we set its value to 1. We change it from 0 to 1. So those are the rules. The main thing here to pay attention to is that the next state is created by applying these rules simultaneously, so at the same time, which means that once we don't take into account the updated value, we only take into account the initial value, which makes solving this problem in place trickier, because all of it's simultaneously, so all of the changes are done at the same time. So birth and deaths occur simultaneously, and the goal here is giving an initial state. For a board, we want to return the next state after applying all these rules simultaneously. So that's the problem. Now let's take a look at one way to solve it is definitely like with extra memory. That would be pretty straightforward. So we have a new board, and then we apply these rules, and get a new board, and then reassign the old board to the new one. So that would be using extra space. Another way to do it is just to have 2 arrays. One for live cells and one for cells that changed from dead to live, and one for cells that changed from live to dead. And we store these in these 2 arrays, and then we do another 2 for loops to change their values in the board in place, right? And so yeah, let's look at that simple solution first, and then we can take a look at a more advanced solution that, for example, that does what's being asked here in the follow-up, which is to solve it in place. Okay, so let's take a look at that solution. I'll just like show it here because it's pretty simple solution. So let's see. So that solution, we just apply the rules, right? We initialize the size, and then we have 2 arrays, one for live cells and one for dead cells, and then we loop through the board. We count the live neighbors for the current cell. We'll take a look at this function later, but it's a pretty generic function that gives us the neighbors of a cell. Now we have the cell, and we apply the rules. If the value is equal to 1, and so basically we apply these rules here, which says that any live cell with fewer than 2 neighbors dies. So that's what we are doing here, and so we add it to the dead list of cells. Any live cell with 2 or 3 live neighbors lives. So here the value doesn't change, so we don't need to do anything. Now any live cell with more than 3 live neighbors dies, so we need to add it to the dead list. So we check, so that's what we are doing here. And then if now for the dead cells, so if any dead cell has exactly 3 live neighbors, which is what we are doing here, then it lives, so we need to change its value to live. So we add it to a live list of cells, right? So now we have the things that need to change, so we can just iterate on this one and this one, and that's what we are doing here. So we iterate on the dead values, the dead cells, and we assign it to them 0, and for the ones that change it from dead to live, we assign their values to 1, and everything else we keep it the same. So this, because we don't change the board here, nothing gets impacted, and all of the changes happen simultaneously, which is what's being asked for us. Now let's take a look at the neighbors function. So we need to look at neighbors horizontally, vertically, and diagonally, and this is what it does it. So 8 neighbors, we have 8 changes, and the way I'm doing it here is this is just to add to the current position to get the neighbor value. So to go left, to go right, we need to add 1 to the to j value, and we need to keep the row value the same. And similar thing for going left, and you can, yeah, that's the same that we are doing here. We just have the values for what we need to add to x and y to get the neighbor, and then we loop through it. We get the new indices for the neighbor, and we check that it's a valid index. That's what we are doing here, that the row is within the bounds of the rows, and the same for column. And then only if it's live that we count it, and then at the end we return the count. So pretty straightforward actually. There are different ways to do the computation for neighbors. You can do a range from, let's say, -1 to 1 for both di and dj instead of doing this, but yeah, all of them work. Okay, so now in terms of time complexity, so we know that this for loop here is of rows by columns. We have at most, if everything was transitioned from being live to dead, then we will have at most of rows by columns, which is the number of cells. Same thing here. So you can see that overall this here is at most 8, right? So it's O of 8. So that's really just 8 multiplied by this, and that's fine. That's still rows by columns. And so overall it's of rows by columns. Time complexity. In terms of space, it's also similar of rows by columns, because live and dead will have at most rows by columns. So we can also say this is just n by m, and same thing for space complexity. Yeah, so this is the solution that just does assimilation and reuses extra space. Next we'll take a look at some other solutions that don't use extra space and modify in place. Okay, so how can we solve this problem? So the main idea here is that we want to change cells that moved from live to dead, and cells that moved from dead to live. We want to change them in place without impacting other cells, right? Because we are moving everything simultaneously, we want for every cell to use the previous state, live and dead states of the other cells, the other neighboring cells. So what we are going to do is we are going to choose new values that mark these two states. That marks a cell that was live and moved to dead, a cell that was dead and moved to live. Because what we want is that for these cells, basically for cells that were live and are dead now, we want to consider them live for the cells they are neighbors of, right? Because we want their original states. And for cells that moved to dead to live, we don't want to consider them live, right? We want to keep them as dead. Okay, so what we are going to do is mark with new numbers, mark this difference, right? So cells that were live and became dead according to the rules, we are going to mark these with the value 3. And cells that were dead and became live, we are going to mark them with 2. With these 2 numbers. You can choose any numbers you want. You'll just have to later in a second pass to put the right values 0 or 1. You would have to check this. So those that were in the second pass, those that had value 2, we will assign value, because 3 live to dead, so we'll assign 0, and those that are 2, because they are live now, we'll assign 1 in the second pass. Okay, so this is the main idea here. So let's run it here on an example. So we'll say 0, right? So the rules that we have is that a cell that has let's pick a cell that will change, like this one. So a cell that has neighbors, so its neighbors that are live, we have this one, we have this one. So basically its live count is 2 here, and it has this one. So these are all its neighbors that are live, so 3. And we know that a dead cell that has 3 live neighbors should become live according to the 4th rule. So we know that this cell needs to become live. So what is this? 0, 1, 2, 0, 1, 2, 3. So basically cell 0, 1 was dead and became live. So it's this. So we are going to assign to it the value dead to live, which is 2. So it's going to be 2. And then let's take another example. Maybe let's say take this one, because this one will change as well. Okay, so this one has how many live neighbors? So it has 1, 2, 3 live neighbors, right? And it was dead, and so it will become live. So this one also will have the value 2. The same thing. Now let's take another maybe example for a cell that was live and turned dead. Yeah, this one. So that one has how many live? So it has this one live, and then has this one 2. We count it as dead. So we count the value 2 as dead in the other state. So this one is 2. So basically, let me write this rule down. So with this we count 2 as dead, because initially it was dead, and we count 3 because 3 represents live to dead. We count 3 as live because the initial state is live, right? And so for 2 it's dead, so we don't count it. And so 1 has only 1 live neighbor, right? So this one has only 1 live neighbor, which is this one. And so its live count is equal to 1. And so this is a live cell with less than 2 live neighbors, so it needs to die, right? So according to the rules. So we are going to, so this one moves over from 1 to 0. Sorry, not to 0, to, because it was live and became dead, we assign 3. And we do this for each one of them. And with this way, basically, what this allows us to do is, for cells that were that are now live, we are not going to count them, because we are going to count value 2 as dead. And so for each state, for each cell, the neighbor count will not be impacted by the changes in place to the board. So that's the main idea here. So this is the first step, would be to do this. The next step would be to just go over the entire board, and values that are 3, move them to 0 because they are dead at the end, and then values that are set at 2, set them at 1. So this is the main idea, essentially. Pretty straightforward once you realize it. And I think this is a pattern also with matrices, where you modify the board in a way that doesn't affect your logic in place, and then you can do another pass to put it in the desired final state. Yeah, so let's code this up and see if it passes test cases. Okay, so now how can we change our solution that we had earlier to take into account this new change here? Our goal is to not use this extra space, and we want to mark those that were alive and turned to dead with 3, and mark those that were dead and turned to live with 2, right? And so let's get rid of these arrays. And so here we want to cell, this cell here needs to be dead, right? We're adding it to dead. So we are going to we are going to just turn it into, since it was live and turned to dead, we want to assign 3 there, right? So we assign 3 to it, get rid of this append here. This one was dead and is turning live, right? Because the cell was 0 and life count is 3. And so we need to assign it the value 1, the value 2, right? And this here sub that was live, but its neighbor's life count is less than 2 or bigger than 3. That cell should be dead, and so we assign it 3, right? The other change is we are no longer doing this. We're going to do something different, which is we'll go do that right now. So for I in range, so we are just going to go through the cells, and those that are set to 3, since they became dead, we are going to set them to 0, and those that are set to 2, we are going to set them to 1. And so that would be rows here, and then a similar thing with columns. And then we are going to do board at I, J. So if the value was equal to 3, then we need to set 0, because the cell became dead. So this would be 0. Otherwise, if it was equal to 2, then it needs to become live, so we need to set it to 1. And that's pretty much it. Another thing is, for the count here, we should not forget that we should take into account those that are set to 1 and those that are set to 3, because 3 in the initial state was live, right? And so this would be N13 instead of just 1. And that's pretty much the only change that we need to make. Now we are not using any extra space, we are modifying in the board. And so let's run it. Okay, so this is an indentation problem. Okay. Okay, so it looks like we didn't change one of them. Okay, this is J, sorry. Okay. Okay, cool. So that passes. Okay, so that passes test cases. Another thing we can do here is, instead of doing this 1 and 3, this is just a simple change. We know that 1 modulo 2 is equal to 1, and 3 modulo 2 is also equal to 1, right? And we know that 2 modulo 2 is 0, and 0 modulo 2 is 0. So basically, for 1 and 3, it's when the modulo 2 is equal to 1. So here, instead of doing this, we can change this to modulo 2 equal to 1. Or in Python, since 1 is true and 0 is false, it's considered false, we can just do this. So that's a small change we can do there. Okay, so this, in terms of time complexity, this solution here is of n by m here, plus of n by m, so number of rows, number of columns being m and n and m. And this is constant. We are doing at most 8 iteration. So overall, the logic here is of n m. So that's the time complexity we have. This is one is the number of rows, the other is the number of columns. And in terms of space complexity here, we are not using really any extra space. So yeah, we are doing it in place, and so this is O1 space. So a lot better than the previous solution. Yeah, so that's pretty much it for this problem. Thanks for watching, and see you on the next one. Bye.